need to count such term because in our case they will be 0. They will be 0. Okay, so I'm not counting it, for example. It's not difficult to count, but I'm not counting it. What would be the last kind of term that will appear in this sum? Why I am focusing on this? Because this gives you an intuition for that actually. The last kind of the terms that can occur is that where all 4 brackets have power 1 and all those 4 are different actually. Okay? All the 4 terms are different. So, in other words, you can have like A, C, D and E. This is one of such example. Okay? This is one of such example actually. And then you can also then count the number of terms. So you can have, so if you have a power 4, you can have only these kind of terms actually. Either you can have, terms with the power 4, terms with 2 brackets and power 3 and 1, terms with 2 and 2, and term with say 2, 1, 1, or the terms with 1, 1, 1. That's it. That's it. Okay? Alright. So now let's get back to what do you call what we have been doing actually. By the way, here in this our population mean is 0. So we are talking about the special case actually. So this is something that we have to keep. Now if I'm gonna expand this, there will be some terms of this form xi power 4. How many terms are going to be there? I don't know. So they are going to be n actually. So it goes from I equal to 1 to n. Then there are going to be some terms of form say xi cube xj where I and j are different. In other words, say I is less than j. So you have a double sum of such terms actually. I is less than j. In other words, I is different from j, x cube and xj actually. I'm not counting for now how many terms are there. I'll later on count the terms that will survive. Okay. Plus, what would be the other possibility? The other possibility would be the term could be xi xj square actually. So the I is less than j. This would also be a double sum. Plus, the other possibility could be say xi square, xj and xk. And this is a triple sum. 1 on I, 1 on j and 1 on k, where I, j and k are different. So this would be another kind of the the terms that will appear in this sum. Okay. I'm not putting any coefficient for now because I'm not at the moment interested in that how many such terms are going to be there actually. Okay, how many such terms are going to be there. Now what would be the potentially last kind of the term is going kind of a term where all 4 indices are different actually. XL and I is different from j, is different from k, is different from L. This is what you're gonna get actually. So there can be only terms, 4 terms of this type, nothing else. Now if I compute say expectation of Sn power 4, this would be same as computing the expectation of this sum. But the expectation of the sum is the sum of expectation. So this would be like calculating the expectation of this sum plus expectation of this sum and so on and so forth. But the expectation of sum is the sum of expectation. So if I wish, I can write this as expectation of xi power 4, sum that goes from I equal to 1 to n, expectation of this times expectation of this times say expectation of this term and sum I less than j less than k, and expectation of this term actually. And now let's think about the expectation of each kind of the term actually. By the way, what would be the expectation of xi power 4? Okay, what would be the expectation of xi power 4? The xi power 4 is, we have assumed actually, I mean if you remember our general assumption that the expectation of xi power 4 is constant, which is clear. We are proving this result under this assumption, so this is going to be k. Okay? Now, what is next? So what is expectation of xi cube times xj? So do you remember something about xi's and xj's, x1, x2? So they are independent. So if they are independent, their functions are also independent. In other words, this would be equal to expectation of xi cube times expectation of xj. But what is expectation of individual random variable? It is 0. So I don't know that whether this term is 0 or not, but this is 0, so this expectation is 0. So all such expectation of this form are 0. What is next thing? Expectation of xi square times xj square would be same as expectation of xi square times expectation of xj square. Now what is expectation of xi square? By the way, what is the variance of xi square? Okay, what is variance of xi square? Or variance of xi? The variance of xi is the expectation of xi square minus expectation of xi whole square. But the expectation of xi is 0. So this means the variance of xi is equal to expectation of xi square. And since your sequence of the random variable is identically distributed, so these variances are going to be equal to each other actually. They are going to be same, so let's call it sigma square actually. So the expectation of xi square is sigma square. So what does this shows? That this is sigma square, this is also sigma square, so their product is sigma power 4. So their product is sigma power 4. What would be the third kind of the term? Expectation of xi square times xj times xk would be expectation of xi square times expectation of xj times expectation of xk, and this is equal to 0. Okay. How about this? Due to the same reason, these expectation of xi, xj, xk, xl would also be 0. So which terms survive only in this? Hence, expectation of Sn power 4 actually. Okay? Which terms will survive in expectation of x power 4? So this I know is k. So the first term is going to be sum that goes, I goes from I equal to 1 to k, plus this goes to 0, this term goes to 0, this term also goes to 0, and this term also goes to 0. So only this term survives, and for this I also know that it is equal to sigma power 4, so I have a double sum that goes like I less than j sigma square. Okay, this is what it is going to be. So hence you can say the expectation of Sn power 4 is Nk plus, now this is an interesting term actually, not sigma square but sigma power 4. This is an interesting term. The question is, how many such terms are there? In other words, how many times I am adding the sigma power 4? I am adding the sigma power 4 as much as times I can have such terms actually. Okay? I can have such terms. So this is a term of the type that I just talked before, this actually. Okay? When you have a square here and square here. So first you need to do what? Out of these n random variable, you have to choose two variables to substitute into these places. So the first is going to be n choose 2. So imagine you substituted what you call xi and you substituted say xj. What is next? The question is, how many terms are going to contain xi square, xj square? So if you, for example, take this term and take this bracket and multiply with it with itself 4 times, then such terms are going to be, for getting the such terms, out of 4 brackets, from 2 brackets I am choosing xi, and from rest of the 2 brackets I am choosing what do you call xj actually. Okay, I am choosing xj. So in how many ways out of 4 brackets I can choose 2 brackets from which I take xi? So this is going to be 4 choose 2. So this is the total number of the terms of this type. In other words, you are summing up sigma power 4 this much number of times. This much number of times. So this term will be n choose 2. So if you are summing up sigma power 4 this much number of times, it's going to be n choose 2, 4 choose 2 times sigma power 4. Okay, this is what you're going to get. And the expectation of Sn power 4 is then going to be, you can simplify this, nk plus 3 times, okay, because this is going to be 4 times 3, 2 times 2, and 2, 2. So it's going to be 3 times of n multiplied by n minus 1 multiplied by sigma power 4. Okay. So far so good. We got this conclusion actually. What is the next thing? And don't forget what was our task. Our task is to show that Sn power n power 4 goes to 0 as n goes to infinity. Okay, this is what that I would like to show. And I'm going to use a previous lemma to show this. One of the lemmas that we proved in our previous lectures to show this. I'll write it in a moment. Now let's think about, let's try to even make this more concrete actually. So you have sigma power 4. If I compute say variance of xi square actually. Okay, where is it? So let's take say so let's compute say variance of xi square. The variance of xi square is going to be the expectation of xi power 4 minus the expectation of xi square whole square actually. Okay. Then I can say what I can say actually. So so I know that the variance is always non-negative. So this means that this difference xi power 4 minus xi square is really, okay, xi square, expectation of xi square is sigma square, so this is sigma power 4 actually. Okay, this is greater than or equal to 0. Okay, this is greater than or equal to 0. And we have also assumption that expectation of xi power 4 is equal to k. So I substituted k here and xi square here, which is sigma power 4. Since this is equal to the variance, so it must be non-negative. So this shows that k sigma power 4 is less than or equal to k. I can estimate sigma power 4 by k. Hence, if I use this fact here in this inequality, I know that the expectation of Sn power 4 is nk plus 3 times of n minus 1 sigma power 4. This is less than or equal to nk plus 3n n minus 1 and what do you call sigma power, not sigma but k. Okay, you're gonna get this. And now let's say divide both sides by n power 4. So let's divide both sides by n power 4. So if I divide both sides by n power 4, so I'm going to have k over n cube. I'm going to have plus 3 times of n minus 1 divided by n power 4 times k. Okay? I can also say, now what is the relationship between n and n minus 1? Okay? For sure n is smaller than n minus 1 is smaller than n. I know that n minus 1 is smaller than n. So I can say that n times, so if I multiply n from both sides, n times n minus 1 is smaller than n square actually. Okay. So I can estimate this. I can say that this is less than or equal to k over n cube plus, okay, plus plus 3 times of n square, because n times n minus 1 is less than or equal to n square divided by n power 4k, which is equal to k over n cube plus 3 over n square k. Okay? And on this now inequality, if I take, say, limit n goes to infinity on both sides, expectation of Sn power n power 4 is less than or equal to limit n goes to infinity, this k over n cube plus 3k over n square. So this goes to 0. This goes to 0. So this is less than or equal to 0. But Sn power 4 is also greater than or equal to 0. So in other words, this limit is also greater than or equal to 0 and less than or equal to 0. So you're going to say that the limit n goes to infinity, expectation of Sn power n power 4 is 0. Okay, so we proved this interesting, what do you call, result actually. Now, if I compute the expectation of this series I equal to or n equal to 1 to infinity, okay, this Sn power n power 4, okay, since these are not growing, so I can say that expectation of this sum is sum of the expectation n equal to 1 to infinity expectation of Sn by n power 4 actually. You can write it in this manner. So there's a little cheating actually that, okay, I know that this is true for infinite, finite expectations, finite sums actually, but it is also true for infinite sums as well actually, okay. If the term, okay, that is representing the series is a stable actually, okay, it is in a stable term actually, okay, so it does not explode. Anyway, this is what that you're gonna get. Then I'm gonna say that this series is convergent actually, okay, this series is convergent. This series is convergent. So if this series is convergent, this is also convergent actually. So this side is also finite. And if this side is finite, let me quote a result and then let's use that result. We quote a result. Which goes like this actually. So I'm now going to use a fact actually that if the expectation of x is finite, then x is finite with probability 1. Okay, so if the average of what you call x is finite, then x would be finite almost surely. So it can't be, you know, what do you call, infinite. So you can't have an infinite x that is infinite but its expectation being finite, because it doesn't make sense. I mean, you have some that can take infinite values, okay, infinite as value, but its average is finite actually. So if expectation of x is finite, then x is finite with probability 1, okay, almost surely. Now, expectation of this series is equal to this series. So this series is convergent and hence finite. Hence this expectation of the series is convergent, is finite. So expectation of this series is finite. So if I treat this entire thing, okay, this entire series as x, what do you call as x, then this result tells you that n equal to 1 to infinity, so x is finite with probability 1. In other words, n equal to 1 to infinity, Sn power 4 is finite with probability 1 actually. In other words, probability of happening this is equal to 1. The omegas for which this will happen is 1. Okay. And then now quoting the result actually, which says that if a sequence, okay, is convergent, if a series is convergent actually, so n equal to 1 to infinity, this is convergent, then the representative of the series goes to 0 as n goes to infinity. So if I take this as a n, I know that this is finite with probability 1. Hence, I can say that the limit, okay, as n power 4, okay, goes to 0 as n gets bigger and bigger and bigger with probability 1 actually, with probability 1. And this completes the proof of the lemma that you need to prove the strong law of large numbers actually. So this is what that was intended actually. Now let's get to the proof of a strong law of large numbers. We have almost done the proof of a strong law of large numbers. The only thing is to just formulate it precisely. It's almost become like a tutorial actually, okay, which I'm getting into every single detail. So, proof of a strong law of large numbers. We know what we know, that limit n goes to infinity as n power n, the sample average power 4 goes to 0 as n goes to infinity. If this is true, or equal to 0 as n goes to infinity. If this is true, then you can also take the fourth root actually. Then this implies that the limit that n goes to infinity, the fourth root of Sn over n power 4, the fourth root of 0 is also true. That is, limit n goes to infinity, the sample average, okay, converges to actual average with probability 1. And this really completes the proof of the strong law of large numbers in the case when expectation of xi's are 0, or if the expectation of some sequence is 0, then this is true actually. Now we're going to do the proof in general case actually. And it's really peanuts, you can quickly prove it. How are we going to say? We're going to say that now assume the expectation of xi is mu, but mu is not necessarily 0. Let's, using this xi, construct xi star. Okay? Define xi star to be xi minus mu. What would be the expectation of xi star? The expectation of xi star is going to be the expectation of xi minus mu, so it's going to be 0. Okay? Now, if I consider the sample average of xi star, I equal to 1 to n xi star. Okay? By the way, this xi star is also IID with expectation equal to 0. Then from the previous case, this case, because this case, in this case, the result says that the sample average, okay, the sample average goes to 0 with the probability 1 of the kind of the random variables which are identical, IIDs, and their expectations are 0. Now we have IIDs xi star whose expectations are 0. So from this result, this converges to what you call 0 with probability 1. In other words, the sample average of xi star goes to 0 with probability 1 as n goes to infinity. Okay? As n goes to infinity. Now, in this, if I substitute, say, this value, which is sum I equal to 1 to n xi minus mu divided by n, okay, this goes to 0 as n goes to infinity with probability